Let's run through some quick MCQs. I'm also going to share this. Can you guess the answers for these? Probably is about 15. The people who actually put together MCQs are the only people who are attending this. Is that how this works? Neural networks are loosely modeled or inspired by. Just shout it out. Huh? 3? Correct. What kind of inputs can be fed to neural networks? Alphabetical, numerical, angular, pretty much anything. 4, pretty much anything. As long as it's numerical, you can pretty much feed anything. That means it's technically numerical in the last point. What features are learned by the red hidden layer, or the hidden layer on to the leftmost? 1, 2, 3. Shout out from 1 or 2 or 3. 3. All right, good guess. Why should activation functions be nonlinear? Because it's so curvy, and hence looks interesting. 2? All right, that's correct. Which activation function is a binary step function? It's a step function. Which activation function is a ReLU? 3, okay, wow. You guys are paying attention. Sigmoid's output value range is -∞ to +∞, 0 to 1, -1 to +1, 0 to 2 to the power 32. Sigmoids, not tanh, not hyperbolic tan. What do sigmoids predict? A probability, right? And what are probabilities bounded? Answer is 2. Which among the following is not an optimization function? Optimization function. An optimization strategy, a function, a technique. Can it be sigmoid? What is a sigmoid? It's an activation function, right? What's an optimization strategy? It's an ability to go back and scale your weights. That's called optimization, right? So hence sigmoid are not optimization strategies. They are activation functions. The fact that you're actually going back and scaling weights, you're back propagating, right? That's called back propagation. And hence, what's the right answer? What is back propagation? You're going back and scaling the weights, but what's the right answer? So it's another, because you need to compute the gradients to see how far the errors are and go back and correct the weights based on those gradients and check to minimize the errors, the answer is 2. Which I didn't cover linear regressions much, but can you guess which one's a linear regression here? Linear is the hint. Well, somebody has chosen a wrong answer. Which is a well-defined graph for linear regression? This cannot be the answer. Who did this? TA. It's this. I would call this the vanilla feed-forward neural network. What graph does it represent? A vanilla feed-forward neural network.
3.
Why is it 3? Yeah, back propagation has nothing to do with going in circles. A graph actually is moving the computations forward, and hence it's directed, and it's directed in one direction without actually trying to go back and do the computation. So it's a acyclical graph. Which of these curves have very high variance? The curves. When you're fitting the curve, you notice that it has a very high variance. Which one has a high variance? What is overfitting? When you actually fit every single data point, it's called overfitting, right? And when you fit no data points, it's called underfitting. When you actually fit every single data point, it's called high variance, and hence 1. All right, you guys passed, which means we can go to the next session, which requires me to talk about some basic recap for what we did last time. In this series, I'm going to cover the classification of grid-like structures. Doesn't necessarily have to be images. We'll call it image classification because image classification represents grids. But technically, when you learn this, you can classify any grid-like structures, time series data, control optimization functions, semantics, if you can somehow figure out how to fit it into a grid-like structure, images. But the easiest way to learn this is to start with images. And as per tradition, one of the most highly influenced, biologically influenced neural network is actually CNNs. For that, I don't know whether it's visible, but I'm just going to walk through the trivia about what you call as the visual cortex, or the neurovisual cortex in the brain. Your brain actually does not see with its eyes. Eyes is only a device which captures light. The concept of sight is given by the brain. I mean, as in your body, or your human anatomy only has a window, and the window is not really a device to see, it's a device to let the lights in. What actually sees is the brain. About half of the human brain is dedicated to vision. About half of your human, it's all in the back, if you notice. And everything else is actually processing information for vision. Seems like vision is very, very important as a fitness function in the world for sensing. Jesus. When images actually fall on the back of your lobe, it's always upside down by the virtue of how the focal length is built. It's the brain which actually corrects it. So you always see the world upside down. 80% of your memories is determined by what you see. This is for people who have vision. Of course, there are other trivias around people who do not have vision and how they actually use a large compute capacity which is not being used by vision, and how they gain other capabilities or other senses because that part of the brain is available, right? The only things that we can see is red, blue, and green, or variations of such. As children, you will not be able to see all those variations. You're born colorblind, and you develop the neural capability to process that information as you grow. All kids, all babies are colorblind. So just buy them black and white toys. Eyes are the second most complex organ after the brain. They're made up of 2 million working parts, about 107 million cells in those 2 million working parts, 7 million cones, out of which 100 million cells are called rods, 7 million are called cones. On an average life, your eyes actually sees 25 million different images on an average, of course. Depends on if you travel, if you don't travel, if you're always sitting in front of the computer. That's the trivia. And convolutional neural networks are literally the most heavily inspired, influenced, biologically influenced neural networks. The agenda for this talk is to actually cover the setup of the convolutional neural network, understand a little. I'm not going to get into too much of math because I know that every time I get into too much of math, I'm losing people. So I reduced the session to 90 minutes. Started 10 minutes late. So I'm going to use the 10 minutes as an extension. We're going to discuss 3 important ideas. If you remember these 3 important ideas, you'll be able to process any grid structures. As I said, it can be NLP, it can be images, it can be time series data. And you just need to understand why the neural networks work the way they work based on these 3 important ideas, and some amount of architectural details in terms of setup, current state. I'm going to do a cool demo, which I'll build. Just as a recap, we spoke about how to encode this, how do neural networks actually encode this concept called knowledge. I mean, how do they really see? How do they know this is a cat or something is a dog or something is a table or a chair, right? We said output of a label is based on the input, what you actually send to it, the grid structure, and some kind of knowledge, which is the weights, which are part of the neural network. They're also called the parameters. Parameters are nothing but the edges between 2 nodes. Nodes are the activation functions. The edges contains the weight or a tensor, and primarily all you're doing is scaling that knowledge or the parameter or the tensor, right? So when you actually send a cat picture and a dog picture through this feedforward neural network, when you send one picture, you're trying to train the network by scaling the weights to choose a label. And when you send another picture, you're trying to train the weight to choose another label. If you try to train the network on the same output with different inputs, both cat and dog, then it starts behaving very interestingly, right? It's A, you're going to confuse the hell out of the network. B, ferrets or any other animals which has combinatorial features of a cat and a dog might actually also be represented as that label that you're training, which is, whatever, label 1, label 2, label 3, right? But technically, that's not very interesting. What you want is image classification. And hence, you go through the exercise of literally training the network. Just as a backdrop, 2015, humans are no longer the best image recognition experts anymore, as of 2015. And what does the concept of best mean? Typically, when you have iconic images which are having animals or objects which are about in a distance, but which are centered, and you show that to a human, the ability for the humans to actually recognize what that image is correctly versus the machines. And these are called iconic images, and this comes through different sample size of testing across different types of humans, and then the error rates are grouped under, let's say, some score, and 5.1% was the human error in recognition. And the machines actually beat that on December 10, 2015 by significantly large percentages, as a delta between 5.1% and 4.9%. And 6 months later, that got beat again, 4.5%. Right now, it's somewhere around 3.6, 3.2%. But machines, I mean, as far as image recognition capabilities go, machines have already outweighed human capability on iconic images. And as far as image recognition goes, when it comes to scene detection is, it's not iconic images. You're not just taking a picture of a cat or a dog in the center, but you just say, hey, here's a scene. Can you recognize everything in the scene? Even in that, it has literally surpassed everything that humans can actually recognize. Depends on how you train the network. I'm going to show you one example that I have built myself and trained. And it's that easy. It runs on a laptop. It doesn't require mainframes and supercomputers. But that brings to the concept of, what does it mean that machines have vision and understanding, right? How do machines actually visualize the world? Literally, they look at the world somewhat similar. I mean, as in they actually looks at zeros and ones and gradients and variations and edges based on filters that you apply, right? In other words, if you have an image and you convert that image to some kind of a grid format, a 3D image into a 2D, literally what the machines see is the numbers behind it, right? So an image can be represented by high intensity and low intensity pixels. High intensity can have high numbers, lower intensity can have lower numbers. Or it can be grayscale versus color, which is RGB, which means you have more than one channel on which the machines actually recognize that image based on those numbers. The feed-forward neural network, which actually accomplishes the task of image recognition or image classification or object detection or localization, has almost a similar architecture. Of course, they vary in depth, they vary in parallelism, they vary in how you actually set up different functions of that convolutional neural network. But mostly when you actually look at convolutional neural networks, you primarily see similar set of functions in its architecture. One's a convolutional layer, and we're going to learn what are convolutions, what is a convolutional layer. There is some kind of pooling, subsampling or downsampling or averaging out the convolutions. And that is repeated multiple times until you actually get some kind of a numerical output which gets connected to what you call as a dense network. A dense network is something that we saw last time, which helped us classify wine. So we built a feed-forward neural network which took some features as inputs and classified the cultivars as outputs, right? So when we are actually talking about neural networks, the final subsampling layer over here, I don't know whether you can, over here, is actually connected to a dense network before it can say what the classification is. Now, it doesn't necessarily have to be a dense network that is connected to a classifier. This can also be a regressor. This output can also be just a numerical number as a prediction, as a stock market prediction, as an index, whatever, right? So you send a bunch of grid-like data, which can be time series data. You're trying to predict some kind of a regression value. It can be an exactly similar setup, except for the fact that you're not training it on a label data or a categorical data. You're training it on series of numbers. So far, so good? Okay. We need to understand each one of this, but the first thing that we need to understand is what is a convolution. A convolution can be thought of as an operation, a simple mathematical operation. To understand the concept of that simple mathematical operation, let's go through an example. Let's assume you have, let's say, a moving object, like you want to track the location of trucks, or you have spaceships and you want to track the location of the spaceship at any given point in time. You either have like a GPS sensor or a laser sensor or some kind of sensing device. Let's also make an assumption that the sensing device is very noisy, as in it's not very accurate. So you want to take multiple measurements before you can accurately predict the location of this device. So the GPS sensor, let's call it the function as the input function. That is, it is a real valued input function. Typically, we are saying that x at time t gives you the real value, a continuous value about the location of your truck. We say that's the input function. But because it's noisy, we are saying we need multiple readings. And we want to take the latest reading as probably the highest weighted, as in we want to do a weighted average across all those readings in such a way that the age, which is the most recent, something that is not really aged, needs to be given the highest weight. We'll call that a weighting function, right, WA. This weighting function is the kernel function, right? The weights, the knowledge of what should be considered the most accurate, let's call it the kernel function. If now you want to aggregate the values, you need to get the area under the curve, because these are real valued functions, right? If x is real valued, time t is real valued, w is the age can be real valued or it can be discrete. Then what you have to do is take the integral of x time t, where you're just saying the weight is a function of time. That is, a being age, t being time. You're saying take the weight, time, current time minus age, and weight it accordingly. That's the integral function. Do we follow this? The reason we are doing this is because this is continuous and real value. But if you want to simplify it, if you say time t is not real as in real value, time t is discrete, I'm going to count time as seconds, 1, 2, 3, 4, bring it to the discrete number, then the function that is helpful for us to understand the accumulation of this weighted value is a summation function. So far, so good? So typically what we're saying is you can think about convolution as this asterisk of input value to some weight. The weight is the one which we're going to scale. That is called the kernel function. That's the filter. We don't know what that weight is. We don't know how to. In the case of this example, we know weight can be based on some kind of aging function. In the case of image recognition, that weight has to be found, and we're going to find that weight based on error rates. Okay. The important part is to understand that it doesn't have to be one-dimensional. Currently, this example shows that time or age is one dimension that we need to work on. But it can also be an image, a two-dimensional image, I and j. So if you actually notice, this equation over here is trying to provide a convolution function, a function which represents two dimensions, similar to this. Here we are having age, but here we are having I and j. We are taking time minus age. We're taking the values of I minus some kernel weight m, the value of j, which is coming over here, minus some kernel weight n. So A is similar to m and n, if you look at it this way. I is the input, k is the kernel. Your indexes for two dimensions are I and j. M and n is the size of your kernel, similar to the size of age. M and n is the size of the kernel. Typically, what you're doing over here is a convolution across two dimensions. You can do a convolution across 3 dimensions, 4 dimensions, 5 dimensions. But it can also be, because it's commutative in nature, you can flip the kernel in such a way that you can, instead of I times k as a matrix, you can do k times I, and also rewrite it this way. This is what a real convolution is. M and m are more predictable, more in control, and more stable. So you actually flip your kernel to get kmn, because m and n is stable, and get the math work similar to the previous math, because it's commutative. From here on, it's just math, right? If you don't understand that, it's okay. You don't have to understand math to actually work on convolutional neural networks. But if you understand this, you can actually go back and rescale your network differently, or have an intuition of why things are working or things are not working because of the convolution or because of another function or feature called cross correlation. Typically, what your neural networks do is not true convolutions. They do what you call as cross correlation. The cross correlation is very similar to convolution, but you're not doing the kernel flip. Kernel flipping uses a lot of compute, or it uses a lot of operational inefficiency. You don't want to do that. You actually use a concept called cross correlation to represent same things. How does cross correlation literally, if you want to get a mental map of what we are actually talking about, what is an input, what is a kernel, what is the cross correlation function, think about this portion over here as your image that has values that is coming in. Think about this m by n as the kernel, or some kind of a window which has some values. You don't know what those values are. Initially, you take random values in it. The idea is the numbers over here in this image does not change, correct? It will never change. I mean, that should not change. But the numbers in this kernel is something that you need to scale. This is the weights. This is the neural network weights. You don't know what those weights are. Initially, you take a random weight, right? And then you compute. The way you're doing the computations is you first you apply this filter over here. You get the output of it, and you keep doing that twice, thrice, 4 times, 5 times, 6 times. So you're going to get 1, 2, 3, 4, 5, 6 different outputs. Are you able to follow this? This is called stride 1. If you did 2 stride, then you would have done 1. Then instead of moving here, you'll move here. You'll do 2, 3, 4. You would have got only 4 outputs. So this is 1 strided. This is your kernel size being 2 by 2, and your stride equals 1. If your kernel is 2 by 2 and your stride is 2, then you get output 4. That is, you wouldn't get this 6 boxes. You'll get only 4 boxes. The way you need to understand what this neural network does is the objective function for the neural network is to actually scale the weights inside this box, starting with a random weight, and eventually moving forward where the error rates for the label is 0.
So you were talking about it, right? And the example is like you move 2 steps to the right. But what about when you move down? What does it go to 2? Is it because of only 3? Or?
You can control that as well. But typically, neural networks cover all rows. Strides are always trying to slide, and you go to the next, and you slide, next pixel, and you slide. You go to the next pixel, and you slide. Strides can also jump. So this is a cross-correlation function, right? This is, as I said, this is not technically a convolution. The reason you don't technically use a convolution is because of kernel flipping, but this has similar outcomes. Unlike your matrix multiplication, cross correlations has similar outcomes. At the end of the day, you're actually trying to fill these boxes. If you have a bigger grid, then you're taking the kernel and you're reducing that bigger grid into a smaller grid on one layer. Then this grid, you can apply some more, kernel functions, and you can reduce it all the way up to one single number. So imagine that if you have millions of pixels and you want to keep reducing that to, let's say, few pixels, you're using the concept of this kernel and summarizing the features as you go forward. That's how you need to visualize this. The way it literally learns all the features is it's going to take all those millions, keep learning the features, and keep going forward until it understands the entire image, right? What does it mean? How does it literally do this computation? So if you have an original image, and if you want to do some edge detection, your edge is some numbers that are filled over here, like some numbers in a sparse matrix with zeros in it, right? Now, if you want to take a filter which has this edge, right? And you actually multiply that filter. So this is the filter which has this edge over here. And this is the original image. When you take the original image and multiply that with that filter, you'll get a very large number because it matches. But if you're trying to actually find the edge over here, you're trying to find something that is actually scaled in this filter, in this original matrix, it wouldn't match and you'll get a 0. Right? So just as a mental map, as a visual image, it doesn't necessarily work that way. But if you don't want to understand neural networks mathematically, but if you want to kind of understand it visually, that's pretty much what's happening. There is some filter, the filter has learned He's learning the features, hasn't learned the features yet in that layer. So it is saying, what's the right feature I need to learn in that kernel? And you're continuously scaling the filter as against the image. You can't do anything about the image. The image is static, right? The only thing that you can actually do is keep changing the features that needs to be learned by that filter, and you'll keep trying to see if there's an edge, if there's a horizontal line, if there's a vertical line, and you keep scaling that on one layer. On the next layer, you'll actually connect all those features to actually make a circle. In the next layer, you'll connect all the circles and big circles and small circles and localize it into a face. In the next layer, you'll probably put the face together with the body, and so on and so forth. It'll be multiple filters because of the way the network is set up.
So, as a part of creating the network, one of the steps is actually to select which are the filters supposed to be used.
The beauty is we don't have to select any filters. We allow the network to learn the filters or the features. So if the question is who designs these features or filters, in the pre-neural network world, we humans used to sit and say, okay, one filter looks like this, another filter looks as a Gaussian blur, another filter is, let's say, edge detectors, another filter is some hue and intensity, another filter. Then we used to design it in the previous world using SVDs, using whatever, right? But with neural network, we say, hey, I don't know what's the right feature to learn. I know this is the image. You go learn those features on the behalf of that image, right? For a given label. But for another label, you learn different features. So the same network, look at the beauty, right? It's not like you're training one network to learn about cat, another network to learn about rat, and it's just on the same network, you're saying, I'm going to choose the output, cat. And I know that everything that I'm going to send across as an input image is a cat. So when you try to take the path towards that label, the way you need to assess and understand this filter is going to be different than when you choose another output, because it's a multi-class output. So if I'm now holding you responsible for another output, the filters that you're going to apply, or the feature maps you're going to apply on the exact same network with the same set of parameters is going to be different. So you can train a single network with thousands of classes by teaching these filters to recognize different features. But the beauty is, if the network is being trained to learn things which have similar curves, similar shapes, then it learns quickly. Things which actually learns more about dogs and cats, when I use the word things, a network which actually learns only dogs and cats, learns them far more efficiently. Now suddenly you throw things which has sharp edges, and if dogs and cats doesn't have sharp edges, you're introducing new set of features into the same network, and you're introducing some kind of noise again, and you have to probably go back and retrain the dog and cat for it to stabilize. You cannot just say, first you learn everything about a dog. Are you done? Now learn everything about a cat. Are you done? Now here's a set of chairs that you're going to learn. Are you done? You cannot do that, because every time you're actually asking the network to learn something, you're also telling the network, like, oh, what did a cat look like again? So it's always better to go back and retrain, right? Because you are using the same parameters and the same kernels and same feature maps for it to keep scaling up and down. Now, coming to the three important concepts the three important ideas which represents a convolutional neural network. We need to understand something called sparse interactions, parameter sharing, and equivariant representations. These are only three concepts any convolutions works on for the sake of efficiency. And when I say any convolutions, any convolutional neural network which is trying to work on time series or image classification or semantic recognition uses this underlying three concepts. Let's start with sparse interactions. Typically, when you actually look at a dense network, when we learned in the last series, you notice that every neuron is connected to every other neuron in the next layer, correct? That is literally a lot of parameters. This edge is called a parameter, right? That's a lot of parameters, which is also connected to the next idea, which is called parameter sharing. But sparsity is because the size of the kernel is smaller than the size of the image, and the output actually reduces the size of the original matrix to a smaller matrix. There is no need for every neuron to connect to every other neuron. It only connects to the next X set of neurons as defined by your kernel. If your kernel is 3 neurons wide, 3 pixels wide, m by n, m being 3, then one neuron only connects to 3 other neurons on the next layer because it is being windowed by the kernel, right? So this is all it has to see. And this one, this is all this it has to see. This one only sees 2 things on the edges. So it is not, the size of the kernel determines the projection onto the next layer. So it's the kernel which projects. What does it mean? That means kernels just occupies about tens or hundreds of pixels. The images can be millions of pixels. And because of these kernels and because of the, the weight that is being scaled within this kernel, the concept of the image, the philosophy of the image, or whatever, the key features of this image can be now summarized using this kernel into a smaller projected space. That concept is called sparse interactions. You don't have to interact densely, you interact sparsely. Think about Occam's razor, right? Eliminate everything that is not an image, that is not a cat, and retain only that which is a cat. That's what it is saying, right? It's almost philosophical, right? It's saying, oh, there's a tree in the back, oh, there's background noise, oh, there's all these colors, and then there is, I don't know, there's clouds, and there's, it says, I don't care, because that never repeats. The only thing that repeats during my training, every time you actually send me cat pictures, the only thing that is seemingly repeating is this pattern. And I'm not going to learn anything else. I'm just going to, the feature map or the kernel is going to just keep accumulating knowledge about what remains every image later. What doesn't copy itself, what doesn't represent itself image over image, it's going to keep eliminating. That's the beauty, right? It applies Occam's razor. There is also the receptive field. There's a projection and there's a receptive field for the sparse interactions. The concept of receptive field is that this H2, H3, H4, sorry. If this is called the projection of this neuron from the previous to the next, then equally there is something called a receptive field. That is, if you take a node or a neuron from T+1 layer, then this is called the receptive field of that node, which is also the width of that kernel. Not only this is connected to 3, but even this gets input only from 3. It doesn't get input from more than 3. This means that the runtime operations, if m and n is very large, is going to be O m by n, right? But because of this receptive field, it's only O k by n, k being the width of the kernel. It is not m by n. And k, the width of the kernel, can be actually chosen to be extremely small as against what is necessary as part of the aging function or the weighting function. So far, so good. What it does is just improve efficiency while computations. There's also this concept called parameter sharing. And parameter sharing is nothing but the ability to literally pass the same weight or the parameter value for activation functions. Where is parameter values used? It's used in activation function, right? Primarily, we said function x or your theta can be xi, wi, right? We're saying x being the input and w being the weight. Typically, the weight is called a parameter, and in a dense network, each neuron needs to have a parameter that's been passed across to the activation function. But in parameter sharing, when you're actually talking about convolutional neural networks, because you're actually using the concept of a kernel, and you're using, I'm going to talk about it, using a concept called pooling, the parameter that actually goes to these three neurons is exactly the same parameter. They're not three different parameters. Those are the parameters that are learned in your kernel. So whatever the kernel learns from the receptive field will be passed across as is to three other neurons. That's called parameter sharing. In a dense network, the value for this parameter is different, the value for this parameter is different, the value for this parameter is different. In a convolutional neural network, there is a kernel in between, and if you notice, what the kernel is doing is actually computing this value for you, and this is a single number, right? You see that that's a single number, that's A times W plus BX plus EY plus FZ, it becomes a single value. They're not 6 values. That parameter gets shared across all the 3 nodes. But in a dense network, each of the weight has to be scaled separately. What does it mean for the computational efficiency? Because X3 shares the same parameter value to S2, S3, and S4, the number of computations it has to do for a 320 by 280 image reduces from 16 billion. 320 by 280 times 319 by 280, 319 being if you're actually, making one stride, as in you're saying I'm using the kernel with one stride, you're just reducing one kernel, right? You're just saying this times this times this time, you're reducing one pixel on the kernel. So it becomes 320 by 280 times 319 by 280. You still have to cover 280 rows. Is 8 billion storage spaces or 16 billion interactions because you're doing multiplication. That reduces to about 200,000 interactions. Just by applying the concept of sparsity and parameter sharing, you humongously, 60,000 times you reduced or increased the computational efficiency to do exactly the same matrix multiplication applying these 2 tricks. In mathematics, if you still do matrix multiplication, if you still do dense networks without applying kernel tricks, you will still get the same output. It is still a neural network which tries to figure out cat versus dogs, but it'll take ages because of millions and millions of parameters it has to compute. So what a convolutional neural network really does is it does exactly the same thing that a feed-forward neural network does, almost similar because it actually brings in a feature map, but does it much more faster and efficiently because of this trick. So the question that David's asking is, what's the trade-off on model accuracy? Actually, there is no trade-off primarily because of the math that we showed in cross-correlation. If you go back to the math and see, is matrix multiplication similar to cross-correlation, which is nothing but a commutative of your convolution, the math checks out that there is no instability. I mean, there's something called invariance and equivariance. We'll learn about it if you're interested in math. There's no it's still stable, it's still accurate, right? And then typically what you're doing is you're just eliminating. So when you actually stride one pixel across, you're trying to look at this image as some kind of a hazy edge detected. You're eliminating. This is the Occam's razor, right? You're pretty much eliminating everything that is not a dog and retaining what is a dog. And if this is what a dog as a philosophical representation needs to be, that's all you're learning by just detecting the edges. You following what I'm saying? The way it does is it just takes that filter. So typically, if you looked at how we used to scale the filter, in the past you had to actually design these filters. You have to say, okay, there is an identity filter which takes an image, and the convolved image would be something like this. Or there is a sharpen filter. If you, I don't know how many people actually worked on Photoshop. Photoshop has filters. That's exactly what it's doing. What a Photoshop filter is that there are predefined filters: Gaussian, blur, sharpen, soften, whatever. It just takes that, applies a stride like what it is doing over here, and builds the feature map. The difference is, in Photoshop or SVD or previous feature detection algorithms, you have to design this filter, which means you have to tell what the values should be in these filters, right? And that is by trial and error. But in neural networks, the values of this kernel is learned through backpropagation. You're following? Okay. The last one is the equivariant representation. I see most of you now perching up in your chair and getting interested. I'm talking about the amoeba-like structure on the top. The equivariant means if there is a change in the input, then there is an equal change in the output. That is, if there is a displacement of 1 pixel in the input, there will be a displacement of 1 pixel in the output. If you're doing time series analysis, if you move X amount of time in the input, you will actually move Y amount of time in the output as well. That is called equivariance. Invariance means that localization of the input is not relevant for the output. It doesn't matter, even if you displace the object, the output will not be displaced. It will be stable, right? In other words, specifically from mathematical perspective, if there is a function fx, then we say it's equivalent to function g if f gx is the same as g fx. Or to visually understand this, if you apply a convolution this way first and some other translation over here, so if you move this way and come this way, or if you apply the transformation first and go this way, the output will be exactly the same. So think about two transformations. First, you actually moved in the first translation, you're actually shifting 1 pixels to the right. In the next translation, you're probably making it much sharper, right? So it doesn't matter if you make it sharper first and shift the picture 1 by right, or you shift the picture right and sharpen it later. The output will be the same. Then we say that it's equivariant representation. What is not equivariant? We say convolution is not rotational in equivariant. That is, if you try to first do a rotation, which requires some kind of a transpose of a matrix, and then apply a translation which is shifting that matrix by 1 pixel to the right, it is going to be completely different than shifting the pixel by the right first and then doing a transpose. We say it is not rotational equivariant, which also means that if you train your images with Kim Kardashian looking straight up this way, and then you send a picture of her upside down, It's not going to recognize her. Convolutional neural networks only recognizes localizations as you train them. If the only training that you're done is cat pictures which is looking straight at you and not upside down, when you send an upside down cat, it is not going to recognize. So what do? Every time you have a picture, you do a trick in convolutional neural network. This has nothing to do with neural networks. Outside the neural network, in your pre-processing pipeline, you flip the picture upside down, backside up, you make it oblique, you kind of play around with hundreds of variations of one picture by creating it if you have one cat picture, you try to kind of give all the dimensions of that same cat picture by working on it in the pre-processing pipeline and then send it to the neural network. The reason we do that is convolution is not rotational equivariant. It's just equivariant from the perspective of the image that is sent as is. It doesn't matter if the image shifts while it is not rotating. It can shift because of the concept of striding. But as soon as you rotate, because your kernel is not flipping, one other trick that you can do, which is execute a different mathematical model where the kernel itself is trying to look at the picture. The picture comes in, then you can make the kernel look at it in many different ways. But that's not computationally efficient, right? Because your kernel is moving top to bottom, with some strides. It's better you keep moving the images upside down, and that is much faster, better, more efficient in terms of pre-processing. And then, of course, it just uses storage space and what you call as iterations. So far, so good. I have 10 more minutes because I started late. I'm going to go a bit faster. The way you need to think about how to stage this is that you have your input layers. You do your convolutions after input layer, which is your convolutional functions. You set up your convolutional functions. And you have your kernel layers, which is actually doing the feature detection. And then there is a concept called pooling that it goes through, which actually reduces the detected feature further. While the kernel actually brings it down to some smaller matrix, pooling or subsampling reduces even further. To understand the concept of pooling, we need to think about it from the perspective of using only the most important feature after a kernel is applied. In other words, I'm going to skip the math. I'm going to come to the downsampling side of it. Imagine after you apply your convolution and your kernels, you come up with numbers like 2, 3, this is 2, this is 3, 1, and 5. Similarly, you have 4, 0, 3, 2, 4, 0, 3, 2, whatever. So if you have 2, 3, 1, and 5, you apply a concept called pooling, which says take only the maximum value in this matrix and move it to the next layer. So only 5 will be chosen from here, and 5 will be copied to the next layer. So it reduces 4 cells into a single cell. So the reduction is called downsampling. So what is the most important feature that I need to take from the cell? Is it number 5? Is it number 4? Mathematically, all you're saying is there is a dominant feature, right? 5 is the dominant feature. 0 I don't have to learn because 0 has no information. 5 has a higher entropy. I'm just going to take 5. So that's called max pooling. You're just taking the maximum number. Average pooling is you average it out. L2 norm pooling is you take the L2 norm, that is the distance, L2 norm distance from 0 to all of those numbers. Or you can also take a midpoint distance to say, I'm going to take the midpoint of this and the distance measure from all of this. Why you choose one versus another is completely based on whether you're using image recognition, whether you're using time series or semantics, as in your linguistics math or some other grid-based variations. Typically, you use max pooling. The reason you use max pooling again is to actually further reduce the network efficiencies, not increase the network efficiency, but reduce the number of computations that's required by retaining the most important feature. Putting it all together, if you notice, there is an input layer, there is a convolutional layer along with some activation function, which is your ReLU activation function that works on the inputs. There is your pooling or subsampling layer, which actually reduces it further by retaining the maximum or the average features that it has learned. And you keep doing that until you get some fewer numbers to work with. And you take that fewer numbers that you have, which can be a single grid, and send it to a dense network for classification. By itself, convolutional neural network does not do classification or regression. Think about it as a Lego block. Convolution, activation, subsampling. Think about it as one box or one complex box. You can do 4 such complex boxes, and you reduce the millions and millions of neurons or input pixels into, let's say, hundreds. Now that you have 100, you can use a feed-forward neural network to do what you want to do. You can do regression, you can do classification, you can fit it into an RI, that is your reinforcement learning, reinforcement RL or RI, and so on, right? The choice of the size of the filter actually has the shape of that dense network. So typically, if you choose, let's say, an output pooling with stride 64 by 64, so with stride 4, then typically you would land up with a 16 by 16 by 64 or about 16,000 units of vector to work with. If you keep changing your strides or if you keep changing your kernel size, then what you land up with on the output to shape your classification or regression will be different. And that is demonstrated here. You can land up with 16,000 units, you can land up with millions of units, you can land up with only 576 units. So size of the kernel, your strides, and the initial size of your input determines what will be set up in your dense layer. These are different types of convolutional neural networks that are in play since 2010, 2012. AlexNet had only 8 layers, if you notice here, which actually won, I think, the challenge in 2012. 2015 is your ResNets, which is at an error rate of 3.57, 5.1 being human accuracy, 3.57 is the accuracy that you have, error accuracy that you have on ResNets. I think that accuracy has, every year, it just gets better and better to a point where it's almost unbelievable, right? To a point where cars can drive itself. Again, if you train it correctly, and if you train it with the side of the truck as well. Challenges with convolutional neural networks, well, it will recognize both of this as a person, primarily because of location equivariance. It doesn't understand this concept of invariance. In a face, it needs to have certain features. I mean, this is an exaggerated example, but as long as you have certain features, it's a face because of the way it aggregates the layers. This is one of the challenges with convolutional neural networks. This equivariance versus invariance is being worked on in a separate neural network called capsule networks, CapsNet, by Jeffrey Hinton. That actually cares about invariance as well. It cares about localization. The current research, typically CapsNet addresses this, invariance versus equivariance. Some of the inspirations that is being taken from biology today is that human eyes is literally low resolution except for a small region called fovea. So why should neural networks actually have high density images? Like literally everything have to be high density, density, right? Can it kind of work with one high density image and a lot of low resolution images? Does it have to work with so many images, like millions and millions of images before it understands the representation? That's another area that is being worked upon. Do we need millions and millions of parameters? That is, do we need such a big neural network with millions of parameters to just learn about cats and dogs? That's another area which convolutional neural networks have been worked on. If I can show you one representation in one particular manner, which if human brain sees this, even if the clouds in the background changes, or even if some displacement that is changes, or if you see like the silhouette of it, the human brain still learns about it. How come neural networks or convolutional neural networks cannot learn about it? And what do you do to make it learn? That's another area that is actually being worked on. And there are many areas. Again, for example, human brain somehow can understand when you look at it, when you look at this and ask a question, is this the same? You pretty much can visualize that. You say, yeah, it is the same. But convolutional neural networks cannot do this. So that's another area that's been worked on in terms of what you call as 3D modeling, or ability to have 3D representation just by looking at a 2D model, for it to visualize that it can be the same in any different angles without training. So far, so good. Almost at the end of the presentation. What I want to do is a simple demo. To do that demo, first I'll take a quick picture of you people just to show that I've written a convolutional neural network which does. 2017, I was working on a project called Cana. I wanted to do a startup. It was a bit crazy. I wanted to build a Iron Man headset. So I thought the first thing I would build was vision. Was thinking about a company called Cana. As part of that, I built a neural network model based on RetinaNet, which uses a concept called ResNets. I have pre-trained it, by the way. So the snapshot, this version 50. I found this version 50. I had trained it on 70 different classes, as in the world, to identify 70 different objects, right? Of course, the more objects I get, the more I can train, but I need thousands of pictures or hundreds of thousands of pictures to train it, to add one more class, but I had done it for about 70. So I'm using that. Typically, this is the layer. It is 50 layers, right? Each of this is an activation, padding, batch normalization, whatever. We're going to learn this as we go forward. But this is just to show how many layers it contains. And I had trained it on these many classes. I trained it on airplanes, apples, bottle, broccoli, bus, whatever, hair dryers, mouse, teddy bears, tennis racket. Don't worry about it. Whatever images I could get my hands on, it was called the COCO image base. Whatever I could get my hands on, I trained it on that. The objective of it is to actually say object localization. That is semantic recognition, scene recognition, not individual cats or dogs. If I take a picture and a lot of things are there in this picture, can I draw bounding boxes? Semantic localization means to literally draw boundaries, but let's say object localization. Can I draw bounding boxes and recognize what those characters are? So I have saved the photo that I just took. I'm going to run my code against that photo. Using a confidence intervals about, so it identifies persons, chairs, whatever. And this is the output. So even if you try to trick it, it identified JR as a person. So you don't need to have a face, JR. You can do away with it. It did not recognize the bottle in the hand for some reason, but it has recognized the chair. It has recognized a dining table, and the rest of them as people, right? Even with Vasanthi sitting in the back. I wish it were. So what I'm going to do is I'm going to reduce the confidence of this. I mean, as in even with lower level of confidence, identify all the objects. So that means the number of objects it's going to identify is a lot more. Where did it? Yeah. So it's somewhere it is saying that it sees a skateboard, but it looks like it's a shoes. It has identified a cup, but I'm not able to. There it is. Where is the cup? But you get the idea. If I say no, only if you're certain by 70%, with 70% confidence, then draw the bounding box. Then it just says, with 70% confidence, this is a person. Notice the reason why this is saying this is a person over here, even without a face, is primarily because it's learning the entire feature. That is hands, fingers, body. So it's saying, as a silhouette, if I look at this, it looks like a person, even if that feature actually did not learn the face. If I take another picture, it doesn't matter, I don't know. It'll take time, but if you guys want to play around offline, if I take another picture, let's see if I have, or maybe I'll just do another quick one. Huh? It did miss 2% because I reduced the confidence. Maybe because she had, let's find out why. Let's say with 40% confidence, right? As soon as I reduce the confidence level, it says, I think that's also a person. I'm going to fix it. There are biases that's built in. Maybe one of the biases can be that I haven't trained it with enough people with probably glasses. I don't know, right? So this explains the bias in training. That if you actually feed only certain types of pictures, it only learns those things. Now you need to do better as a community to train this differently. I might take another picture, probably with the bottles, I don't know, to demonstrate. I don't know, yeah. Get closer.
One of the most impressive things there is chair. Think about how diverse chairs are. It's pretty wild.
I had close to 10,000 pictures of chair available as a data set. So it's also access to the data set that I had, right? This is the last one, and then I'll open up for questions. So there's no reason for me to load the snapshots again. I could have just, it recognizes this as a cup over here. I think it also kind of putting a bounding box over here, but I can't read whether it's a bounding box around the chair or the cup. But this, it clearly recognizes a cup. It recognizes a bottle over here, if you notice. So the things it has recognized is bottle, chair, person, chair, a lot of chairs. It just loves chairs for some reason. There's a lot of chairs out there. A laptop, oh, that's interesting. And I can actually reduce or increase the confidence of this. If I reduce the confidence, I'm gonna say, even if you're not very sure, tell me what's happening in the scene. So you can kind of, in scene detection, you can say with 100% accuracy, but with minimal accuracy, right? The things it actually has detected over here is dining tables, which is about 0.3, TV, I don't know where. No, it is, we just can't read it. Oh, no, not in the other room. It's TV over here. Oh, it thinks this is TV at 0.34%. It thinks that device over there is TV. But anyway, you get the idea. The bias is what you inherit into the system. The confidence intervals is what you actually build as an output. It is a 50-layer neural network, 70 classes. It identifies, just if you're interested, this as a last example. I had a picture of I asked my son to actually do something. and to trick it or whatever. So he came up with this idea in 2017, by the way. He doesn't look like that. He's not very proud of this picture. This is what he did. The funny thing about this is it thinks most of this is a banana, except that one part of the banana is a frisbee. Explains location equivariance. It is not trained for invariance. For some reason, it has always learned that the things that are trained as frisbees are all either slanted in one particular way, of a particular color, of a particular shape. But the same thing which is slanted the other way, it is not stating it's a frisbee. Notice the bias. I don't know why. I mean, we can theorize this, but hence the bias, right? And it identifies Spock and Captain as person, which is in the background. So that is Star Trek Beyond. It goes there and says, oh, there are people in there. And it identifies this area over here as a TV, while the TV is this entire region. So there was, Apple TV has that. So it says only the top portion is the TV for some weird reason, right? So I played around with many pictures, and it's funny things that it does. I can show it to you offline. But that's the power of a simple neural network that I built on this laptop with one GPU in 2017 with about 10,000 to 100,000 images across 70 different classes. Imagine what research teams can do, right? You can take as an exercise, as a workshop, a simple neural network, which can identify just a cat and a dog. And I can help you over the next few weeks and also come up with a code of a very simple neural network which identifies a cat and a dog as a homework. Does it sound like fun? All right, either way, I'm not going to put up the code for this. I'll put up the code for the simple neural network, a convolutional neural net, which just classifies an image as cat or not cat. How about that? And that will give you some ideas in terms of how to understand convolutional neural nets. Thank you, guys. Appreciate it.